So we were somewhere in part 4 of the module, physics of molecules. So let me remind you of the problem. The problem is that we put two nuclei fixed at a distance r, and then we only have one electron. So the problem is something like, do I have the Hamiltonian? Yes. So the Hamiltonian becomes a single electron kinetic energy. The electron sees the nucleus A, sees the nucleus B, okay? And the two nuclei repel, okay? When I grade the midterm, I'm quite disappointed to notice that many of you didn't realize that the plus minus sign has some meaning as an attractive, repulsive, it seems random signs to me. Okay, so it is very basic. It has happened. It has it should have been included in first year in your the first EM course, and then another EM course, and then when you do the hydrogen atom, when you do a lot of simple physics. Okay, so it is rather surprising mistake. Okay, so this is the problem. We only have one electrons to see whether it can form a binding curve to bind to protons. So we try to solve this problem, but in a very clever way. We don't want to solve it all over again or numerically. We rely on our knowledge of atomic states. We have hydrogen states. We know the hydrogen 1s, we know the hydrogen 1s. We are just solving about the states. The second step is to fill in the electron. So when we solve the state, you don't need to worry about you only have one electron. Why are you using the atomic states of the lonely proton on the other side? It's not that problem. We are looking for energy eigenstate of this system. And we are using the 1s or 2s, 2p of each atom as the basis to expand our unknown wave function that we can carry out a variational calculation. That is the foundation of the problem. So when we do that, the idea is that, let me go to the hydrogen page. So we have a hydrogen on the left side. So we use a 1s. This is the 1s ground state wave function, again, given to you in the midterm problem 6, okay? So this is the 1s on the left, and we have a 1s on the right. So the simplest possible idea is just to invoke these two atomic orbitals, and then form the linear combination of them as a good approximation to be the energy eigenstate of the H2 plus molecule. Whether it is good or bad, we have to compare with experimental values. But by physical insight, we only have one electron, and we are looking for the ground state. So some of you may want to invoke the 2s of each atom. Fine. If you do that, you will be doing a linear combination of 1s, 2s of the left atom, 1s, 2s of the right atom. You are linear combining 4 atomic orbitals. Therefore, you will get at the end 4 eigenvalues. They are 4 molecular orbitals in order of increasing energies. But think about it. You only have one electron. Thereby, at the end, when you fill it in, you will be filling in the lowest energy one. Then, naturally, you may think, when I include the higher but empty molecular orbitals into our calculation, will it affect the accuracy of the ground state? And will it affect the complexity of the calculation? So they are competing factors. So in doing quantum mechanics, it's always a balance between accuracy on one hand and also the computing effort on the other hand, okay? Some of you may even want to include the free 2Ps, 3S, 3P. Of course, that will be more accurate, but that will be much more effort, okay? So here, I simply invoked 1s on the left and ignore all the 2s there. Another reason is that 1s and 2s in hydrogen, they differ in energy by 10 eV. You can easily use the standard formula minus 13.6 eV divided by n squared to make an estimate. And even by simple perturbation idea, you know that so high in energy to 2s would not affect this lowest molecular state formation much. The most important one will be the 1s and 1s of the two centers. Okay, so it is these ideas supporting our proposal. Simply use 1s, and done. So it's the simplest basis of two atomic orbitals. So the idea is to linear combine them. So I have the left 1s, right 1s, and linear combine them. In principle, I should have two different coefficients, C1 here, C2 there, okay? However, in this particular case, it is even simpler than that, for the reason that they are the same center, proton, proton. So I see it this way, and I see it the other way, this way. So I'm moving my head to this side. Literally, they are the same situation. So you cannot, well, the electron cannot possibly bias one side or the other. Thereby, we note one thing. The two coefficients squared, if I put two different coefficients there, they should be the same, all right? So thereby, there can only be two possible linear combinations where the coefficients are the same, that I pull it out, or the coefficients differ by a sign. So I also pull it out, but with a minus sign. So you see, one is a symmetric kind of linear combination. By that I mean, I'm referring to the midpoint between the two nuclei, and actually is an inversion. It is a 3D problem that what I refer as a symmetric or even or odd, okay? But even if you don't follow my last sentence, I hope that at least you can follow why the two coefficients, the magnitude must be the same, because proton left, proton right, they are the same thing. However, if you are doing hydrogen fluoride, hydrogen bromide, they are different, and then you cannot make use of this simple, this simplification. So let me continue. If you do that, pictorially, 1s plus 1s is something like this. You add them up, okay? So this is the case when the separation is big. It's already decay, you know, Bohr radius is the decaying length. So if you square it, it's something like that. For the minus linear combination, the wave function is something like that. If you square it, it looks like this. And you see that for last separation, it doesn't make much difference. The key difference comes in when the separation is not that big. Let's say the separation is something like 1 to 1.5 angstrom to 2 angstrom. Now that is the right ballpark. Think like a physicist, hydrogen atom ground state, 1s. the 1s state is exponential minus the radial variable r divided by Bohr radius. Thereby, the extent the wave function goes out is about Bohr radius or 2 Bohr radius. It's exponentially decaying. So in order for two atoms to form a molecule, their wave function must detect each other's presence. So the nearby atoms are you there? Okay, you are there because I sense my wave function overlap with your wave function, thereby there is some overlapping region. And by that simple picture, you know, the bond length is usually of the order of this kind of numbers, okay? You never see it like 10 angstrom bond length. If they are that far apart, they are isolated. They don't care about each other, all right? So, I mean, numbers have meaning. So if you consider such a smaller separation that is around the ballpark of bonding, the plus combination, the wave function looks like this. The point is, it is decaying from the left, it is decaying from the right, but it is not falling to so small in the middle. And these two add up to be slightly bigger in the middle, okay? So that's the point. You square it, it is still not zero in the middle, all right? However, for the minus combination, the left decay to a certain extent, the right also decay to the same extent, but if with the minus sign, they completely cancel at the midpoint. So therefore, you have a node at the midpoint. In 3D, it is called a nodal plan, okay? Because it's a 3D problem. I'm drawing it as a 1D picture. If you square it, then the difference is very clear. There's no probability of finding the electron at the midpoint for the minus combination, while for the plus combination, there's an enhanced probability of finding the electron around the middle between the two nuclei. At this point, for those who have taken some chemistry courses, you already sense that this is a covalent character. So just put all the pictures together, you get this. Left-hand side is the plus combination. That will be called bonding, because now I think you already see the covalent character. So that is the bonding side, left side. The right-hand side will be called anti-bonding linear combination. And that is the meaning of LCAO. We are linear combining atomic state from the two atoms forming the molecule. So more quantitatively, we can set up the 2x2 matrix. I have an appendix setting that up. I will discuss it in a while. Here is just the schematic, lead you through the answer. So 2x2, because you have this variational trial wave function, then you can set it up as a 2x2. So you have a 2x2 problem to solve, and you want to solve for the eigenvalue. Okay, thereby you will have two values. One is the plus, at the end, one is we refer to the plus combination, another refer to the minus combination. So you have two energies, all right? Remember, there is a repulsive term between the two fixed nuclei that we need to add back after we get the answer. And that leads us to this picture when we stopped discussing last time. Here, I want you to look at two lines in particular. Look at the epsilon plus as a function of R. This is the bonding, the plus linear combination when we vary the separation R of the two nuclei. Okay, so this is the answer, but that is not the whole thing because there is always a nuclei-nuclei repulsion line, this solid line. It is just a number for a fixed separation R because you put it there, then I know what is E squared over R, okay? So the whole thing, we need to add this electronic answer to the nuclei repulsion value. So we add this term, this line, to this line, okay? And at the end, we have this E plus R. Now, this is the important line, this one. Follow my cross, go down as a minimum, and then go up a little bit, okay? Now, at this point, you already see one electron can really form a binding potential energy profile. By that, I mean, you see a well around here, and there is a preferred separation. So this distance is the preferred separation. That will be the lowest potential energy, okay? And then there is a certain energy gained, the depth here, okay? If the two protons stay at that preferred location and the electron do the plus linear combination, that is to say, do the binding, do the bonding MO, bonding molecular orbitals. We have two answers. The other one, only the electron one is this yellowed line, but we have to add back this nuclear repulsion, and the end result is this yellowish E minus R, okay? We see that for this particular case, I must emphasize this, for this example of H2 plus ion, this curve does not have a minima. And historically, because of this is called the anti-bonding state. It is kind of opposing bonding, okay? But we only have one electron. So the ground state is that the electron will like to fill in here, this particular state, and then never mind about the anti-bonding state. So I take the two resulting curves out. So this is the one that I introduced. The electron energy separation, different separation, add to the nuclear repulsion. So you see that well. So you have a preferred thing, distance, that will be the bond length, and then you gain a certain energy by doing so, okay? So the numbers are, you gain that much, and then it is 1.1 angstrom. That is about the right ballpark, right? Half a angstrom, a bore radius on the left, from the left, a bore radius from the right, you add it up, is about that number, okay? Common sense, all right? But it is high level common sense. So let's get back to some chemist picture. So we have discussed the quantum physics of this particular H2 plus ion bonding, and how do the chemists represent this result? Usually, it is done like this. You will see such pictures everywhere in chemistry books, and actually in physics books on atoms and molecules. So the two on the right and on the left and on the right refer to the 2,1s atomic orbitals, minus 13.6 eV. You may think about that this way, okay? Meaning they're not yet forming the molecular orbitals. And from our consideration, we realized that we have a 2 by 2 matrix. So it's like minus 13.6 minus 13.6 delta delta, okay? Delta delta star. So one is pushing down, another is pushed up. Roughly, it is this physics, simple. 2 by 2 split fighting matrix mass, okay? So you see, the one is suppressed in energy is the bonding molecular orbital. The one that has a higher energy is the anti-bonding atomic molecular orbital. What I mean is this one. So now you may take the 0 as minus 13.6 when they're far apart, okay? And therefore, one is lowered, another is pushed very high, actually here somewhere, okay? So you see that. So at this point, we are still talking about solving the Schrödinger equation and get the state. So after getting the state, we take the electron into the problem and fill in the state, fill it into the states. We only have one electron, so ground state, it must go to the bonding one. It doesn't matter up or down, it's a lonely electron, okay? So, and then you immediately see, by doing so, some energy is gained, okay? That is the 2 point something eV. Therefore, H2 plus is stable relative to single hydrogen neutral atom and a lonely proton, okay? So, and you see how powerful one single electron can do. It can cleverly use its wave function to bind 2 centers, 2 protons, okay? And in the lab, you can make this. Then I would like to go to the appendix so that I can clearly illustrate that this bonding is a quantum business. So this is the detailed version of the H2 plus problem that I just discussed, okay? So there are similar equations, but I would just like to show you the whole calculation, not every detail, but at least the key points so that you appreciate bonding is very quantum mechanical. Some of you, from secondary school or lower form chemistry course, you often have this classical physics idea saying the electrons stay in the middle and then using Coulomb interaction so as using the Coulomb attraction of the left nucleus and the right nucleus, so it gains some energy by having 2 centers attracting to it and all those stories, right? Now is the chance for you to learn what bonding is correctly, right? So it should be an important part of your training. So I will use the atomic units for simplicity, but to start with, let me show you the full SI unit Hamiltonian, okay? So we started from that. Kinetic, 1 electron only, you don't have 2 terms, 1 term. Electron sees the left nuclei, the left nucleus, electron sees the right nucleus, and then Coulomb repulsion between the 2 nuclei. For simplicity, this is the atomic unit version. Now, we set up the variational calculation. So we know what to do. A is 1s on the left, B is 1s on the right, okay? So we do a linear combination, then we go back to the first week of our course. You have a Hamiltonian, you have a trial wave function like this form. You don't need to derive everything again, copy the result out and do physics, okay? That is how physics students should do. You don't waste your time, repeat all the derivation all the time. But you really have to collect this thing into your mind, all right? So now this is the 2x2 problem to solve. At this point, I haven't made any simple approximation like, okay, let's say SAB is 0, SAA is 1, okay? At this point, no. Keep everything general. Just to remind you, for example, what is HAA? So it is 1s left, 1s left, and then the full H in between. So this is the whole thing inserted in the middle. So this is HAB. Similarly, HBA, you will have 1s on the right, the full H, 1s on the left. So this is what it means. Again, let me remind you, SAA is simple. 1s on the left times itself, integrate all space by normalization, it is 1. So we know this answer exactly. However, SAB is something tricky. You have 1s on the left, multiply into 1s on the right at a certain separation, integrate over all space. In principle, it is not 0 because there's no quantum mechanical rule saying that it should be. All we can say is that it is SBA star, and you give me a separation, it should be a function of the separation. That is easy to see. Both sides are dropping. If the separation is small, then they have overlap, and then when they have overlap, this will not be 0, okay? However, if the R is big, both are exponentially decaying. When they don't have any overlapping region, the product will be 0 everywhere. Then that will be a 0. Therefore, this integral must depend on R in principle, okay? So it is time to look at how quantum this whole business really is. So let's work out a few matrix elements. For example, HAA. I have 1s on the left, 1s on the left on both sides. Then I need to insert the whole Hamiltonian. So the whole Hamiltonian is what I wrote in blue, okay, for your convenience. So I just separate the 4 terms. For the reason that you realize this term is the hydrogen problem of the left-hand side. So this is the hydrogen Hamiltonian of the left atom. When it operates on the 1s ground state, it gives you minus 13.6 times the state itself. And then this number comes out and you will have a 1 normalization of the two-wave function, okay? So that is easy. I represent it by E1s, and actually you know the number. The more interesting thing is this term. This is complicated, thereby, for simplicity, I just represent it by a symbol, but I know one thing. This physics is, I see this left 1s times left 1s, this is left 1s squared. Therefore, it has classical physics interpretation, right? This is the probability of the electron residing on the left. And when it sees the nucleus on the right, there will be some attractive energy. And this is the first term. Well, the last term is just for decoration. It's just a number, you take it out, all right? And then a normalization, you get 1. So this is just the constant repulsion that we add back at the end. So we include this, all in all, this whole integral will be a function of the separation R. So I call it J. For those of you who have done problem set 4, then you realize that you have seen similar things in the helium excited state. But there is a difference. But the difference is that in there, there is only 1 nucleus. Okay? But you see a similar thing called J, the Coulomb integral. Now, more interestingly, let's look at HBA. What I mean is that this off-diagonal thing. Okay? Now, look at this. I do the same trick. The difference is that I have left 1s and right 1s on 2 sides. And then the Hamiltonian has 4 terms. I also, again, I write it into 2 terms in one integral, other 2 terms in another integral. That's the whole complete statement, no approximation. The same trick. I see this giving me minus 13.6 times the ground state. However, this is left, this is right. After you pull the minus 13.6 in the number out of the integral, this remaining integral is our S. It's not 1, it's S, okay? It may be 0 if it's far away. Now, the more interesting thing is the second integral. Now, first of all, I give it a symbol called K. I don't want to evaluate it, but let me tell you, this can be evaluated for hydrogen state, exactly, analytically, I mean. Secondly, it depends on the separation of the 2 nuclei. Okay, naturally, rather. So I call it K of R. Third, more importantly, you must realize that this is a single wave function on the right, star. It is a single wave function on the left, 1s. And then you do not see same wave function squared. No, you don't see that, okay? Thereby, you don't have the interpretation of it is a charge density. You only see one factor of the left wave function and one factor of the right wave function. You cannot make use of Born's interpretation to relate to something classical like charge density in your E&M interpretation, okay? The point is, this K integral, also called exchange integral, is entirely quantum. That's the whole point, okay? Just like what we met in helium atom, in the excited state discussion. It doesn't matter. You add that back. Well, it's a number anyway, right? So you add that back. I call it the whole thing K R. It's still legal, right? Is that okay? Okay. But the point is already there. Okay. The point is already there. The most important thing is that in particular this term, you don't know how to interpret it. That's the point. All right. So let's see how K plays the role in bonding. Okay. So we have a J and we have a K. Okay. So let's write down the whole thing. I'm going back to the 2x2. Now, after working out HAA, so HAA is this. I have it minus E SAA, which is 1. Okay, you follow me for this element? Similarly, for the one down here, because they are symmetrical. I see it this way, it's A on this side. I see it that way, it's B on that side. So with that, you don't need to repeat the calculation. Now, the more interesting thing is the off-diagonal element, AB element. We just work out HAB, which is minus 13.6 E1S times this S, the overlap integral, left and right, plus the whole thing called K, which is a function of R, and then minus the unknown eigenvalue times the overlap integral S. Similarly for this BA, okay? I think I'm lazy about this star stuff, okay? So it doesn't matter, just take it this way, all right? Now, I want to illustrate it is K that matter. That's the whole point. Okay, so I announced the result. Now I justified my claim. The whole thing now becomes solving for the two eigenvalue E, for the two values of E, the energy. All right, so we don't want trivial result 0, 0. We don't want it. So the determinant vanishes. All right. We have done that in problem set 1. This is the easiest case because it is epsilon, epsilon, something like delta, delta. Okay, so you do that. E satisfies this equation. Okay. E is on the left side and on the right-hand side. So you solve for it, you will get this formal result. One, you see that it is minus 13.6 that form the basis. Now that is the chemist's two lines out there, all right? And then one value has J plus K over 1 plus S. Another has J minus K over 1 minus S. So everything is involved. All right. So you have two answers. Let me remind you, J is a function of R, K is a function of R, S is a function of R. So everything is a function of R, thereby we know this as a function of R. That is our curve at the end, right? If you plug this answer back, let me see if I can do that. Okay. So if you plug this eigenvalue back into 2x2, you can solve for this thing. But if you already did problem set 1, you know for this situation, you have this answers, as we already expected by symmetry. So at this point, I would like to briefly discuss this overlap integral S here. It's a function of R. So formally, this overlap is 1s from the left, 1s from the right, you integrate over everywhere, okay? So it depends on whether they have a region when both functions are not zero. Just to remind you, each function decays rapidly using ball radius. So it's very easy for this integral to be zero. If the separation R is 5 angstrom, it is zero. Decay there, nowhere along any place, this integrand is non-zero, okay? I mean, when this is not zero, this is zero. When this is not zero, the other is zero, right? So now let's see why we have this kind of different denominator. So when I have the plus linear combination, all right, I mean this one. If I work out the wave function for this, I know they are the same, thereby I have this combination. Then it remains for us to do is require this to be normalized, thereby we can find this C plus constant coefficient. So this is the physical requirement. The LCAO, the bonding state form should be normalized. And plugging in this linear combination, we have 4 terms, okay? We have the left times the left, integrate over itself is 1, the right, okay? Then we have these 2 overlaps. These are the S and S star, but they are real numbers, so SS doesn't matter. So I have 2 plus 2S. This is the constant we want to find the normalization constant. So I have that. This must be equal to 1, okay? So I get this normalization constant being related to my overlap integral. So if you think it is 1 over square root 2, it is already an approximation. That's the point, okay? In principle, the plus and minus 1 has slightly different normalization. The plus 1 has this, the minus 1 has this sign being minus. Nonetheless, when the separation is not very close, if you approximate S to be 0, then you have 1 over square root 2, what many students would have guessed. But let me tell you, this thing, if you plug in 1S on the left, 1S on the right, that can be done analytically, and this is the answer, okay? But that justifies our discussion. When R is, if you write it back in SI unit, this is minus R divided by the ball radius. Okay, this is in the atomic unit. Thereby, what we said is valid. When the separation is longer than a few ball radius, the exponential already killed everything, then this overlap is 0. But it is generally non-zero, okay? So with this, we can go back to our 2 answers and illustrate how quantum bonding is. Just take a final look at these 2 answers, okay? Now I want to use picture to draw it out. If only we retain the diagonal term, then we have this 13.6, 13.6 minus, okay? But when we have the off-diagonal, meaning they couple, they try to form bonding or an anti-bonding state, we found these 2 answers, okay? I'm anticipating, and that's true, K is negative. Thereby, I have this one being the lower one. Nonetheless, you get 2 separate values. That's the point, okay? We just argue that when the two nuclei may be 2 bore radius, 3 bore radius apart, this S is not going to be big. Okay, now this is given by this formula. You can plug in if R is 2, so E minus 2, then times this, just a number of order 1 is not going to be big. Therefore, if we take the approximation that as the overlap is 0, it's even clearer. Now you see, one energy that is the lower one is minus 13.6 plus whatever the J integral gives you plus K integral. The other one is minus 13.6 plus J minus K. And that's the point I want to make. J is not the key business. The one that has Coulomb classical interpretation is not the one term that is crucial for bonding. That's my message. The one that is crucial for bonding, that is to say, give you the bonding and anti-bonding state, is actually the K integral. You see? Okay? So the difference in energy in bonding and anti-bonding is actually 2K. It's K that matter. J, although exists very complicated form, you need to do the integral. It is not the one that is responsible or crucial for giving us bonding in nature. And at this point, I really want everyone here to appreciate quantum mechanics really is the theory for the existence of matter. And that is, I think, if you try to find anything in 20th century that is profound in humanity, not only in science, in the knowledge of human being, it is one, I will rank this very high on the list, at this top 5. Okay, so this is a very profound result, consequence of quantum mechanics. 人類的大智慧20世紀, okay, it is really highly non-trivial. I encourage you to try to explain this to your younger brothers and sisters at home, if they are doing high school, okay, telling them that it is very quantum. Nothing like what you learn. The electron is in the middle, a Coulomb, so double Coulomb, very happy, stable, that kind of thing. It's not like that, okay? So I already explained what I want to say. So it is very quantum. It is this term that is crucial, and it is very quantum, okay? We have the J around, but you see the J come in through the same side. Okay, I mean this. So it's not going to be crucial to distinguish the bonding and the anti-bonding one, and J has classical interpretation. Here, I just flash you the analytic result. For those of you who really like mathematics, you may go home and start from the expression and try to prove this, okay? Sometimes I will ask the TA to do one of them for you so that you see how to proceed. It is not difficult. It is similar to some helium atom integration, but now it's 2 centers, okay? But doable, very doable. These are analytic exact results for the 3 integrals in atomic units. Thereby, another good exercise is not to try to derive it, accept them, but plot them out, right? By that I mean, you have this. this is half H3 minus half H3 in atomic unit. And now you have this integrals, thereby you can plot all this as a function of R easily. And this is the answer, okay? So now you see the answer emerge. What I show you in the main text now come out more analytically. So here I draw 3 curves. What I draw is the following. I'm trying to draw the bonding one only. So this is a constant, I don't care, minus 13.6 or half H3. I have a J term, so I can use J over 1 plus S. Of course, you can do it by something like mathematical plot, and then it's all come out. So let's see the second term. This is this dashed line. Okay. And now the third term, you have a K, right? And I think what Mr. Au said is about this thing. So now you see that? Okay, are you there? All right. Okay, so it's still there. It's still there. Okay. So now what I'm saying is that you can take the expression as given, K over 1 plus S. You take this S and then use your numerical or Excel to plot it out. Then you get the other dashed line. The whole answer is a constant that I take this as the minus 13.6. This is this first term, a constant, plus this, plus that, and then you get the blue line. And that is the bonding curve we brought out at the beginning of today's class, okay? And at this point, you get all this old business again in chemistry textbooks, okay? And I hope at this point, at least you have the understanding, the simplest example of molecular orbital theory. This minimum forms a bonding MO, bonding molecular orbital. And then when you have a number of electrons, you want to fill them in according to the Pauli exclusion principle. In this case, we only have 1 electron, so we can put that in, okay? And this is the whole thing about LCAO. Now that is the process, and the answer are called MO. So you will see linear combination of atomic orbitals hyphen molecular orbitals. That is the meaning of these symbols. It is the most popular method in doing molecular physics problems, even up to now, okay? Of course, there are something called first principle calculation, solve the whole Schrodinger equation numerically, but usually you lost the physical sense. You only get a lot of electron density out of the calculation. You cannot trace the origin of this bonding. So this analytic investigation. So finally, I would like to introduce the big names of this business. The 2 big names, and there is a third one really big behind this, okay? The 2 big names are Robert Mulliken and Hun. We have mentioned Hun many times, but he never got the Nobel Prize for strange reasons. He contributed a lot to quantum physics of atoms and molecules. So they worked together at Göttingen. Their teachers, their teacher was Max Born. So Born was really the big engineer behind all this whole thing. So he assigned this problem, Hun did this one, okay? Understand molecules, and then they did. Among the three of them, Mulliken got the Nobel Prize in chemistry, 1966, and the citation of the Nobel Prize reads, for his fundamental work concerning bonds, that's what we discussed, and the electronic structure of molecules, that's what we discussed. The formal name is, you understand the wave function of electrons, that is called electron structure of molecules, by the molecular orbital theory, okay? Somehow, Hun was still alive at that time, but he was not awarded the prize. And Mulliken at that time actually said he would be very glad if the prize was shared with Hun. Born was another exceptionally talented physicist, slightly older generation than Heisenberg, Schrödinger, and Dirac. Maybe same age as Schrödinger, but certainly maybe 12 or 13 years older than Heisenberg, Dirac, and Pauli. He actually supervised Heisenberg's first papers in quantum mechanics. Heisenberg did his PhD with Somerville, but on the topic unrelated to quantum physics. Well, Somerville was a more classical people, so he assigned it a problem in classical physics, I think related to fluids, to Heisenberg, and Heisenberg somehow did his PhD work and graduate. But during his PhD work, he visited many times Max Born in Göttingen. So Heisenberg's interest was really in quantum mechanics. So the first papers with three names, so Heisenberg, Born, and another Heisenberg's student, I forgot the name. No, I forgot the name. And then Heisenberg by himself was awarded the Nobel Prize 1932, 100% of the prize by himself. And then 1933, the prize was awarded to Schrödinger and Dirac, 50%, 50%. And these two Nobel Prizes were announced at the same time. So in 1 year, there was no announcement. The next year, two announcements, including 1932, 1933. So Heisenberg was rather embarrassed. There are letters from Heisenberg wrote to Born after the announcement. So Heisenberg just apologized to Born that somehow it's out of his control. The Nobel Committee might have made a big mistake, things like that, okay? So nonetheless, after 20 years, 1954, Born was given his well-deserved Nobel Prize. The citation was rather interesting or funny. The citation was referring to his interpretation of the wave function square as a probability. But certainly, Born has done a lot more. Actually, the matrix mechanics of Heisenberg, Born was 100% behind that thing. Okay, so that is how physics, Nobel Prizes worked anyway. Okay, so so among these three, only Hun was eventually not given a Nobel Prize. I think he passed away in the 1980s. Okay, so I stop here and take a break of a few minutes. Okay, then we come back and discuss more about bonding.